right, that'll work. All right, so we left off here talking about the 3 different ways that water can be taken up by the root. We had that capillary movement, the root to soil contact, and root extension. And remember that we said that, when water's there, it's gonna kind of fill out just like you would a sponge, but that as the sponge or the root starts to dry, that water starts to move away from the root, there will be a little area like a cavity, or the water will not be in contact with the root anymore. So next, moving into the hydrologic cycle and kind of this how the water gets to and from. This is kind of some interesting stuff if you really think about it, that the water that we have on this earth cannot be created nor destroyed. It's like the matter that we have, that's in a whole different subject area, but still, the matter cannot be created or destroyed. So the same amount of water is here. We've had the same amount this whole entire time for the most part. It's just in different reservoirs. It's in our clouds. It's as water vapor. It's in lakes and streams and rivers, in our backyard creeks or whatever. But the same amount of water has always been here. It's just taking a different form, and that's why we don't have it in our aquifers anymore. So we have things, we break these down into watersheds. I know I'm probably not telling y'all anything new, but going over this is kind of standard from the book. We have these watersheds that kind of the boundaries, and so everything within this watershed kind of drains to a central point from the highest elevation to the lowest elevation, kind of like a bowl. And that we have different watersheds in each state, and then each state has different watersheds, and ultimately they have different areas within those states and watersheds known as water resource regions. And so here we are in Tennessee. This is where I'm from. So we have this lower Mississippi, all these different watersheds, and they all pretty much drain out of the mouth of the Mississippi. If we put those into the bigger ones, kind of like this is our bowl where everything drains down to where I'm from, kind of out the coast. The problem is with this is that all the nutrients that are spread in Montana, that's that Montana, a little bit of North Dakota, Minnesota is a large agricultural production. All the nitrogen that they're applying goes into their rivers and streams, and all the nitrogen in Nebraska and Kansas go over to Missouri, everything in Missouri, everything in Ohio, the Midwest Corn Belt, and then deposits in the Gulf of Mexico. Deposits in the Gulf of Mexico, and so in Mississippi, in the Delta here, we kind of get a lot of flack for spreading too much nitrogen because we grow a lot of corn, cotton, and a few other crops as though like we're the bad ones, but this is happening all over the country, and so all of this is kind of coming down our chute and then ending up in the Gulf of Mexico. And that's a pretty big issue. So we have a water balance equation. Anyone in wildlife and fisheries? Anyone in forestry? Interested in forestry? Environmental studies? If you're going into some sort of water management, hydrology of some sort, you'll be using equations like this, and each one of the components of this equation has an equation that has some subcomponents of an equation, and it looks like a water taxonomic classification of equations. Which kind of makes a little sense. We have our input, which is going to be the precipitation is going to equal how much water is stored in the soil, how much is discharged into the streams, and then how much evaporates. So we have the same amount of rainfall in Tennessee. That hasn't changed over time, but the frequency and the distribution of that has. And so more evaporation from increased temperatures changes the weather patterns, and so we have more rainfall in these clouds as they're moving across the country. Probably more a meteorology class, but still to understand that change in the distribution of that rainfall really influences how we manage our lands and our resources. There are 5 fates of that precipitation. It can be intercepted, so trees or buildings. If it's not intercepted, it will infiltrate. So remember, that's breaking just this top surface layer of the soil, so infiltrating into. Once it infiltrates, it can percolate through the profile. Runoff, which is a big one. And so the problem with the runoff, or why we're seeing more of that, is because the intensity of the storms that are coming, the distribution of those storms is faster than the infiltration and percolation rate of our soils. And so we like to see this nice, slow, long rain happen so that it just kind of drizzles a little bit and that water can make it all the way through. Dr. Morris was telling me that he had, in Red Bowling Springs, he hadn't had any rain in a long time, like all summer. And so when Ida came through, there's just this big blob of light green that came over, and he's just sitting on his porch just thinking that there's some rainfall coming onto his land. But it was nice and slow and steady, and so it was able to fill that soil profile up, and some of his hay crop is saved. So it's stored in the soil, and if we're lucky enough, we can get it to come all the way down into the groundwater so that we have at least something to drink and bathe ourselves with. So within interception, we have 3 components: stem flow, through fall, and canopy drift. So interception is going to be when the water hits the tree, or a bush, or any type of plant material. It could be a corn plant, might be a cotton plant, soybean. It could be in a nursery. It could be in whatever situation, blueberries, it doesn't matter. So this is when the rainfall hits some plant, and that plant is going to intercept, obviously, that rainfall and then change the way that it flows into the ground. So some of the things that can influence how those plants affect the infiltration or the interception of that rainfall. So for the red arrows, at the top of the tree, it's going to hit those leaves. That water is going to disperse and it will run down the branch and then run down the trunk of the tree all the way to the ground. And so most of that water is going to end up right here by the trunk. What happens to all this water out here? Hard, fast rain. What happens to the water?
Runs off.
It runs off, exactly. Some of it's going to infiltrate, but there you go. He's like, hold on now, can I get in Delta Tau Alpha?
Hey, does that count for bonus points?
That count for bonus points. So, you know, it's only gonna infiltrate a little bit, but most of it's gonna run off. And so we need to have if we can cover our grounds more, we can intercept more of this rain and give it time to infiltrate our soils. This in here, and so deciduous trees are going to have more than coniferous, and this is because of the shape of their tree top, kind of like an umbrella or an upside down umbrella. And so the more surface area that rain hits, but we have a pine tree that is fairly straight up and down, and its branches are almost 90 degrees. There's not enough intersection, and you know, they're not very tall. I mean, wide and upright. So the architecture and the way that those trees are set up, this Spartan juniper is not going to intercept as much water as this large oak tree is. Making sense, Jack? Okay. It's just kind of like the things to think about. This might go into, if you're, have any of y'all taken Dr. Baer's class, the technology and natural resources? He's like, yeah, that's the reason I'm not in Delta Tau Alpha. She's like, exactly why, right? But these are some of the, y'all are doing curve numbers and what type of things we're supposed to, and runoff, and he's having flashbacks.
Stressful class.
He's having flashbacks. It doesn't get any easier. But like going over all those different types of things that we can do in order to conserve our resources, our natural resources, this water. We don't have any more of it, but we need to keep it when it happens. When it goes into the atmosphere through evaporation and falls down, we need to contain that. If not, it runs off into the ditch and goes out into the Gulf of Mexico. We very rarely get that back, or if we do, how do we get that water back? Think about the things that happen in the Gulf of Mexico that produce a lot of rainfall.
It's a hurricane.
Hurricane, right. And so what happens when we have hurricanes? We have damage, right? Comes through and it blows everything away. So if it makes it to the Gulf of Mexico, it comes back in a bad way, or it could come back in a bad way. It takes a very long time for that water to make it back to us. Next we have throughfall, and these are the raindrops that actually kind of make it through and miss the leaves, because it's not always perfect. Those are some lucky raindrops to actually fall through an oak tree and not hit. Or maybe there's a strong rain that happens and there's so much water that it can't flow down through stem flow, and then just actually there's so much water that it just drips out of the tree. And there are a few things that influence that, how many leaves are there, what type of precipitation it is, but mostly this intensity and duration. So if we have a light rain that happens really quickly, that tree is able to quote unquote adsorb with a D some of that water and capture it, and then that actually moves into stem flow. But if we have a very fast and a very hard rainfall, some of that might make it to the ground as throughfall. And then finally, canopy drift. And so that's the stuff that on the edges of the tree that actually make it to the ground. We talked a little bit about this previously when we were talking about soil and water. We have gravity, that capillary action, and that porosity. And going back to soil texture and architecture, what do y'all think some of the things are that are going to influence how fast water moves through a soil?
Texture.
Texture is going to be one of them. The bulk density, correct. The structure, and how much organic matter we might have there. Because that organic matter acts like a sponge as well, and it is going to absorb some water. Runoff, also known as overland flow, and this happens when the rainfall intensity is greater than the soil infiltration rate, which is affected by bulk density, texture, structure, and organic matter, and the way that that soil is. So what we're trying to do is plant more cover crops so that we can influence the structure in the top 6 inches of soil, so that we can create more pore space for more water to infiltrate. Or maybe you might see some, trying to think of where the last place I saw this. I know I saw some out at Shipley, but you might see them put, those straw mats over at like a newly built roadside or, over new construction that hasn't been seeded yet. And that's so that they can intercept some of that rainfall and slow it down. So one of the main purposes of cover crops is to adsorb some of that impact and slow down or intercept that rainfall. Intercept the rainfall, stem flow down. I know it's only a little clover plant, but we still have stem flow there that makes it down to the soil. We might plant like some sort of mulch around our trees so that that stem flow keeps that water in the ground and it doesn't evaporate back out. Or something to slow that rainfall. No-till, we leave our no-till, our ground's no-till, we leave the residues out there so that we can capture some of that water rather than have it run out the field and cover crops. Again, we're back to this field capacity, our psi, the potentials, the water potential being much greater outside at the top of the tree than it is in the soil. And so that is going to influence how much water comes out of the soil, not into it. So we need to have these trees to help the water come in the soil so it's not pulling it out fast enough. There's like a very delicate balance between how we plant those trees or our crops in relation to the atmosphere. And so that as we get to permanent wilting, so we have a rain and our plants are full, and then we get to permanent wilting point and there's no water, which means photosynthesis slows and plant growth decreases. Our crops are, so we're like, oh, farmers are out there sweating it out. They're like, oh my God, when am I gonna get some rain? Okay, cool, so it rains, like it just 2 inches in an hour, but that doesn't help them any, because bless you, because most of that water ran off. So the difference between evaporation and transpiration, evaporation comes from a water body. Bless you again. This is like a lake, stream, river, pond, creek, ocean, whatever. Transpiration is that comes through a membrane or a pore. Someone here is from Arizona. Is that you? So, do y'all know why they don't sweat in Arizona as much as we do here? As much.
Humidity?
The humidity, but when the water actually evaporates, when they sweat, because people are sweating, that's transpiration. Like in Mississippi, when we sweat, it just beads up on our skin because there's so much humidity, and so there's like this boundary layer that I'm gonna come back to this, right? So this is what it's like in Arizona. The moisture content in the air is less than what is in our bodies. So when we sweat, because the potential is more negative in the air, it evaporates or transpires very easily. In Mississippi, that's not the case. We have a very hot, like we're at 0.6 bars. And so there's like a boundary layer, and this also goes back to our plants. So if you have a whole bunch of plants together planted in Arkansas or Memphis or some area, and it's really humid, you have all these plants that are trying to perspire, but the humidity is so much that the water can't go anywhere. So we need a wind, a breeze, to move that air so that the water can evaporate out of the stomata. So how much water is in the atmosphere affects how much water is going to transpire. So more humidity, less water loss. Low humidity, more water loss. That's why they can't grow anything out in Arizona except for cactus. That's it. So evaporation is from a water body, transpiration is through a membrane or a pore. It's the easiest way to remember that. I think we're gonna call it right there. We'll get into more calculations later. Y'all have a good weekend.